So these are the laws. Newton's laws. Newton's first law of motion is an object in motion will remain in motion, and an object at rest will remain at rest unless acted on upon by a force. Newton's second law of motion, net force is equal to mass times acceleration. And Newton's third law, for every action, there's an equal but opposite reaction. So, explanation 1. In this first example, we are testing the idea of inertia, which is defined as an object's resistance to changing speeds through the balancing of a card on our thumb along with a coin on top of it. As we balance the card with the penny on our thumb, both objects remain at rest until this is changed as the force applied by the flicking of our finger acts upon the card. As a result, the card leaves as it is horizontally launched, while the coin remains at rest in the same spot it was in, considering that the flicking action only imposed a force on the card and not on the coin. Hence, the card experienced an impulse imposed by the flicking of the finger, kicking it into motion and changing its momentum. On the other hand, the penny on top of it remained in place, considering that its inertia kept it in place as the card, despite the changing speed of the card below it. Explanation 2. In the next clips, we are once again considering Newton's first law as well as his second law, but this time looking at variations of mass on top of the playing card. For the two varying masses, I chose a dime for the video on the left and a quarter for the video on the right, to test the idea of their inertia as the card is flicked from underneath each. As both trials were successful, it was clear that objects that are heavier with more mass, such as the quarter, are more resistant to change over than that of the dime, which was lighter with less mass. The card's change in speed as it was flicked and launched horizontally had little to no effect on the coins, but could be seen to be affected by the mass of the coins. With more mass, the acceleration/speed of the card seemed to decrease as compared to less mass, which increased the speed of the card. Explanation 3. In these examples, we are examining the idea of objects in motion with changes in mass. In the video on the left, we have one bottle cap placed on top of the bottle as it is set into motion until it is abruptly stopped by the books in the way. As seen in the video, the bottle cap stayed in place and in motion as it traveled in the same direction as the bottle continued in. Hence, objects in motion will continue to be in motion. As stated before, the more mass an object has, the more inertia that the object will experience. With the addition of more mass on the bottle, the objects above the bottle, as it is in motion, will have a higher resistance to the changing speeds of the bottle as it is in motion. When it comes to the direction of motion, these objects will resist the changes as we see in the video on the right as they fall off before the bottle reaches the stopping by the books. Explanation.
Yeah. In this video clip, the ball goes around the dent of the plate at a constant velocity until it falls through the edge of the opening. Once at the edge, the ball is pulled towards the ground by its weight. Force is applied to the plate to cause a slide round motion to move the ball. This is part of Newton's first law. This law says that an object in motion will remain in motion and an object at rest will remain at rest unless acted on upon by a force. The velocity of the ball increases as it falls off the plate. Once it touches the ground and bounces, velocity decreases and increases again. This is part of Newton's second law. This law says that the net force is equal to the mass times acceleration. In this video, Newton's third law is at test. This law says that for every action there is an equal but opposite reaction. In the video, there is a stronger pull of the band when the full water bottle is hanging. This is because of its greater weight. There is a greater pull on the full bottle. When the half-filled bottle is hanging, it is hard to balance because its weight is less. The pull of the rubber band is less than the full bottle. Overall, the pull of the half-filled bottle is less. When pulling apart the two bottles with approximately the same force, there is a higher stretch on the side of the full bottle. The reason for this is because the full bottle has a greater mass, therefore it needs a greater force to move. The rubber band stretches more. The rubber bands are pulling inwards while the water bottles are pulling outwards. The direction is opposite.